Hello everyone. In this video, I would like to talk about a metric d on x, and its corresponding d over 1 plus d is also a metric on x. So here is the problem. Show that if d is a metric on x, then d bar equals to d over 1 plus d is also a metric and that it is equivalent to d, i.e. the identity map it from a metric space xd to a metric space xd bar is a homeomorphism. We are going to split this problem into two parts. The first one is d bar equals to d over 1 plus d is also a metric. The second part is d bar is equivalent to d. Let's get into the first part. D bar equals to d over 1 plus d is also a metric. Recall, a metric space is an ordered pair xd where x is a set and d is a metric on x, i.e. a function d from Cartesian product x and itself to real number r, such that for all x, y, z in x, first, d of x and itself equals to 0. 2. X is not equal to y implies d of x and y is larger than 0. Third, d of x and y equals to d of y and x. Fourth, d of x and z is smaller than or equal to d of x and y plus d of y and z. So consider d bar equals to d over 1 plus d. If d is a metric, it means that d satisfies all of the conditions that we mentioned above. Then we have the following. First, d of x in itself equals to 0. Then d bar of x in itself equals to, by applying the definition of d bar, we have d of x in itself over 1 plus d of x in itself. But now we know that d of x in itself equals to 0, so we can write the next step, 0 over 1 plus 0, which is equals to 0. Second, d of x and y is larger than 0 for x is not equal to y. Then d bar of x and y equals to, again we apply the definition of d bar, then we have d of x and y over 1 plus d of x and y. But since d of x and y is larger than 0, it guarantees that the whole expression is also larger than 0. Third, d of x and y equals to d of y and x. Again, we apply the definition of d bar, we get the second expression, but since d of x and y equals to d of y and x, we get the third expression, which is d of y and x over 1 plus d of y and x, and we use the definition of d bar, then we can go back to d bar of y and x. Fourth, d of x and z is smaller than or equal to d of x and y plus d of y and z. Again, we apply the definition of d bar. This time, by applying the triangle inequality, we'll get the second expression is smaller than or equal to d of x and y over 1 plus d of x and z plus d of y and z over 1 plus d of x and z. Now we have three different cases we need to consider. A. If d of x and z is larger than or equal to d of x and y, and d of x and z is larger than or equal to d of y and z, then we have d bar of x and z is smaller than or equal to d of x and y over 1 plus d of x and y plus d of y and z over 1 plus d of y and z. It is because d of x and z is larger than or equal to both of d of x and y d of y and z, which makes both of the denominators smaller, which in turn makes both of the fractions bigger. And now we can apply the definition of d bar, then we'll get d bar of x and y plus d bar of y and z. B. If d of x and z is smaller than d of x and y, then consider d bar of x and z, which after we apply the definition is smaller than d of x and y over 1 plus d of x and y. It's because when d acts on two different elements, it's always larger than 0. And when we consider this fraction, if we increase d of x and z in both the numerator and denominator, then the whole expression will be larger. And after we apply the definition of d bar, we'll get d bar of x and y, but obviously this is smaller than d bar of x and y plus any positive numbers. And so in this case, d bar of x and z is smaller than d bar of x and y plus d bar of y and z. Similarly, C, if d of x and z is smaller than d of y and z, then basically it's the same argument as B. We'll get the triangle inequality for d bar also. Thus, d bar is also a metric because we already showed that d bar also satisfies all of the conditions for being a metric on X. Now it comes to part 2. We need to show that d bar is equivalent to D. If you remember the problem, we have another way to put d bar is equivalent to D, which is the identity map xd to xd bar is a homeomorphism. Now recall, let m1 equals to x1 d1 and m2 equals to x2 d2 be metric spaces, and the function f from x1 to x2 be a bijection such that f is continuous from x1 to x2 and f inverse is continuous from x2 to x1, then f is a homeomorphism and x1 and x2 are homeomorphic. Since we know that xd bar is also a metric space from part 1, and it is obvious that the identity map it is a bijection, the bicontinuous property of it is the only thing left to be shown. Again, we need to recall some definitions. This time is the definition of continuity, specifically continuity from one metric space to another metric space. Let m1 equals to x1 d1 and m2 equals to x2 d2 be metric spaces, and f be a map from x1 to x2. Then f is continuous if and only if for all x in x1 and for all epsilon in R+, there exists delta in R+, such that for all y in x1, d1 of x and y is smaller than delta implies d2 of f of x and f of y is smaller than epsilon. So now we are going to show that it and it inverse, both of them they are continuous. For it from xd to xd bar, for all x in X and for all epsilon in R+, there exists delta in R+, such that for all y in X, we have the first case, for all epsilon in from 0 but not including 0 to 1 but not including 1. Delta equals to epsilon over 1 minus epsilon, which is in R+. Now, how to get delta in terms of epsilon is by using the definition of d bar. I'm not going into the detail of this, but you can try it by yourself. It's just a trick by finding out d of x and y in terms of d bar of x and y. Let's continue. Then d of x and y is smaller than delta implies now we have d bar of it x and it y equals to, now I apply the definition of d bar and also the definition of an identity map, then we'll get d of x and y over 1 plus d of x and y. And now we apply the condition of d of x and y is smaller than delta, we'll get the larger fraction delta over 1 plus delta. Now applying the equation of delta equals to epsilon over 1 minus epsilon with a little bit of basic arithmetic and simplification, then you'll get the final expression epsilon. And thus we show that d bar of it x and it y is smaller than epsilon. But this is not the whole story, because we only cover from 0 but not including 0 to 1 but not including 1. How about from 1 including 1 to positive infinity? Because we require for all epsilon in positive real numbers. So we have the second part for the map it. Again, the same map with the same conditions for all epsilon in from 1 including 1 to positive infinity, and delta in R+, but this time delta doesn't have any restriction. We'll see why that is the case in the following steps. D of x and y is smaller than delta implies, again, we have d bar, it x, and it y. Applying the definition of d bar, we have the following, the second expression. which is smaller than delta over 1 plus delta. Since we know that delta is in R plus, and by looking at this expression delta over 1 plus delta, since we know that if delta is approaching to infinity, then delta over 1 plus delta will be approaching to 1, but it will never be 1. But in this case, because for all epsilon, they must be starting from 1 to positive infinity, it means no matter which delta we pick, it's always smaller than epsilon. So combining part 1 and part 2, we prove that for all epsilon in R plus, there always exists a delta in R plus such that for all y in x, d of x and y smaller than delta implies d bar of it x and it y is smaller than epsilon, which means it from xd to xd bar is continuous. Similarly, we can do the same thing for it inverse, but we don't need to split it into two parts. For it inverse from xd bar to xd for all x in x and for all epsilon to in R plus, there exists a delta which is equals to epsilon over 1 plus epsilon, which is in R plus. Now we don't need to worry the non-permissible value of epsilon because all epsilon are positive real numbers, such that for all y in x, d bar of x and y is smaller than delta implies d of it inverse x and it inverse y equals to, this time we apply the definition of d in terms of d bar. Again, you can try to do the basic arithmetic to change the subject from d bar to d. Then we'll get d bar of x and y over 1 minus d bar of x and y. This is smaller than delta over 1 minus delta. Again, it seems counterintuitive, but we need to understand that because delta is restricted by the expression of epsilon over 1 plus epsilon, so although all deltas belongs to positive real numbers, in fact, delta is restricted to from 0, not including 0, to 1, but not including 1. But we only need to find one such delta to prove it. So we don't need to include all of the positive real numbers. So if that is the case, delta is from 0, not including 0, to 1, not including 1. That means the expression delta over 1 minus delta, when delta is getting larger, which means closer to 1 but not equal to 1, then the whole fraction will get larger. Now we can plug in the equation delta equals to epsilon over 1 plus epsilon, then we will get epsilon. So in this case, we also prove that it inverse is continuous. So conclusion, the first part, we show that d bar equals to d over 1 plus d is also a metric by showing that d bar of x and itself equals to 0. If x is not equal to y, d bar of x and y is larger than 0. D bar of x and y equals to d bar of y and x. And d bar of x and z is smaller than or equal to d bar of x and y plus d bar of y and z. The second part, we prove that d bar is equivalent to d, i.e. the identity map it from xd to xd bar is a homeomorphism, which means the identity map satisfies the following three conditions. The first one, it is a bijection, which is trivial, so we didn't show it. B, it is continuous. C, it inverse is also continuous. Thus, we solve the whole problem. End of proof.